Okay, problem 4, we have these two children playing a game where they basically cock this little spring-loaded gun here and they pick some, some compression amount to set it to. Oops, let's see. Let's call that X, okay? So they cock it by an amount X, and then it springs off the table and it goes a distance D before it hits the ground. And they're trying to land it in this cup or box or whatever it is, okay? So, I want to look at 3 different states of the system. They don't give us much information there. What they give us is they say when it gets cocked by this much, it goes this far, and then they say, well, we really want it to go this far. So like the first time you cock it by so much and it lands here. So they want to know how much should you really do it by to make it land, in the cup. And so they don't give us much information. They don't tell you the, in fact, I'm just going to, let's say I'm going to do in green. No, I'm going to do in orange. I'm going to do the things they don't tell you. They do not tell you the spring constant here. They do not tell you the height of the table. They do not tell you the mass of the ball. They don't tell you, yeah, well, that's what they don't tell you. So there's a lot you have to sort of intuit on your own, and a lot you have to sort of do symbolically and have a little faith that things are going to work out. So let me draw for you the states of the system I'm going to look at. So state 1 is going to be when you're on the table. When you're cocked. So when you've got this, let's see, when you've got this spring cocked from its rest position by a distance X, and the ball is in here, okay? This is going to be state 1. State 2 is going to be when the spring's been released, and the ball is, let's see, the ball is going off the top at a speed v0. So, and that's all horizontal, of course. Okay, so this is the spring before launching, and this is just as we're about to go off. And then we're going to look at what happens if you go off, at some speed v0 here. How does that relate to D? So let's start by seeing, how if we launch at a speed v0, how does that relate to the distance D we go? Well, what happens is that the ball comes off and it takes some amount of time to fall, and when it falls, when it hits the ground, however far it's gone horizontally, that's our D. You'll remember that the ball is only accelerating in the y direction due to gravity. Remember, the ball is in projectile motion, which means it starts off with some velocity, but the only force acting on it is gravity. That's our definition of projectile motion, which means the ball's acceleration is simply straight down at a rate of g. Okay, so the ball, whatever horizontal velocity the ball starts off with, it keeps. Okay, so the ball has the same horizontal velocity here. So if we say, I'm going to call t sub f is the time of flight, or maybe I should call it time to fall. That's the time it takes the ball to fall. And that does not depend on this initial velocity coming off. All that time to fall depends on is the height and g, and then however long it takes gravity to accelerate it down and smack it into the floor is time to fall. But it can be moving horizontally or not. It can be moving horizontally at any speed, in any horizontal direction, left or right, or forward or backwards if this is a 3D thing. But that's not going to affect the time it takes to fall as long as it's not starting with any vertical velocity. So what we get out of that is that the distance traveled, this capital D, you travel horizontally in the air from the base of the table, is going to equal your initial velocity times the time it takes to fall. So this is just how much time it has to move horizontally. This is the velocity it has horizontally, and then D is how far it actually goes. Okay, so TF is a constant. Doesn't matter how much we cock the spring, TF is the same. So let's talk about this V0 here. That's what comes out of this energy balance here. So in this situation here, in state 1, we start with kinetic energy. We start with spring potential energy. And at state 2, we have kinetic energy, and we have spring potential energy. So at the beginning, this is when it's cocked and it's motionless. So kinetic energy is 0. Spring potential energy, it's been deflected by this amount x. So this is going to equal 1/2 kx squared. What's K, you ask? It's the spring constant. And you say, I know what K is, you jackass. What is the number for K? And I say, well, actually, we don't know. They didn't tell us. We just know there's a spring here that behaves like this. We've just got to take on faith there is a spring constant, and it's K, and we can't do anything about it right now. We can't do anything about the fact that we don't know it right now. Okay. Now in stage 2, it's got kinetic energy. It's going to have 1F mv0 squared, and it's going to have spring energy, but the spring is returned to rest, right? So the spring is now at x equals 0. It's back at its rest position, which means the spring has no potential energy. So at state 1, EMEC, total mechanical energy, is 1/2 k x squared. At state 2, EMEC is 1/2 mv0 squared. So if energy is conserved from 1 to 2, then we're going to have 1/2 k x squared equals 1/2 mv0 squared. That's just conservation of mechanical energy from 1 to 2. Say these are equal. So let's set these. Let's work a little harder at these. We want to find v0 in terms of everything else. So that's going to v0 squared equals, the 1/2s cancel, and we get k over m times x squared, which means v0 equals square root of k over m times x. Okay. Now, what can we do with this? Well, recall over here we found how v0 interacts with time of flight to determine the distance you can go. So we put those together. We're going to plug this value of v0 into here. So then you're going to get d equals square root of k over m times x times the time of flight. And if we rearrange this a little, remember x is our cocking distance. That's something we can control. K is the spring constant. That's a constant. We can't change that. M is the mass of the ball. Can't change that. And TF is the time it takes for the ball to fall, which we also can't change. So I'm going to rearrange this to put all the things we can't change first on this left-hand side of the equation. Okay, so all of that times x. This stuff, we don't know any of these numbers. But we do know is that they don't change. These don't change from one attempt to the next. So I'm going to give this a name. I'm going to call this capital A. I'm going to say capital A equals square root of k over m times TF. And from our first, and so then you can say, hang on, I got to do my parentheses properly. Then you can say d equals capital A times x. So capital A is what we found is our parameter that relates the amount you cock it to the distance it travels. So let's look and see what our first attempt was. The target is 1.8 meters away, and the first compression is 1.10 centimeters, but the center of the marble fell 26 centimeters short. So for the first attempt, so let's do this in, I don't know, let's use brown. Okay, for our first attempt, the distance it traveled was, and I gotta look at this again, 1.8 meters minus 26 centimeters. So 1.8 minus 0.26 minus 0.26, which is going to equal 1.54 meters was our first distance. And x was 1.1 centimeters, which means it's 0.011 meters. So d equals ax, well, 1.59 meters, that's this formula here, d equals ax, right? I'm plugging that in. I'm plugging stuff in over there. So this d equals a times 0.11. Oh, sorry. Going 0.011 meters. And that means then a is going to equal 1.59 divided by 0.11. 0.59 divided by 0.11 is going to give us 14.45. Okay, a is 14.45. So, is that right? Hang on. 0.011. Sorry, 144.5. There we go. So 144.5. Let's erase that. There we go. Okay, so now for our actual attempt, where we want to get it in the ball, which is 1.80 meters away, we take let's see, we take let's do purple again. We take d, so d equals ax. D equals ax. We know our a is 144.5. We know d is 1.80 equals 144.5 x. Okay, so I hope that's, I realize this is not very legible, but best I can do. Sorry, 1.80 divided by 144.5 is going to equal, so we want to compress it 12.45 centimeters. 12.4 or 12.46 centimeters. Okay, so x equals, or sorry, 0. Wait a minute. I think it was 1.10 centimeters, and so 0.01246 meters. Okay, 0.0246 meters. But they want it in centimeters, so 1.246 centimeters. So let's hope. No, I got it wrong. Okay, what did I get wrong? So let's see. 1.80, 1.54. So this really should come out to just be a ratio, proportionality. So let's see. Let me try cross multiplying. 1.80 slash 1.54 times 1.10 centimeters. 1.28. So I must have missed a key somewhere. So it's actually 1.286. Well, let's try this. Okay, well, I got it wrong somewhere in the first attempt. Whatever. No bonus points for finding that.